Hey everybody, Mr. Piercy here, and we're going to be looking at our last two segments as they relate to triangles. So just to quickly review, we've so far discussed mid-segments, which are segments that connect midpoints of triangles together, or well, really just midpoints together. They don't have to be inside of a triangle. And we've also established that for mid-segments that they're parallel to the third side of the triangle and they're half as long. Then we've talked about perpendicular bisectors of triangles and the point of concurrency that they make, which is called the circumcenter. Then we talked about angle bisectors and the point of concurrency that they make, which is called the incenter. And now we're going to be looking at medians and altitudes. Now, if you haven't already done so, you might want to just go back, or you might want to pause this and head over and watch the video that I made demonstrating, the points of concurrency for medians and altitudes. Particularly for the medians, because they have some very specific math attributes that we'll be using. Anyway, let's go ahead and move on for what we're looking at today. So here are the definitions of the segments that we're going to be looking at. Median simply goes from the vertex of a triangle to the midpoint of the side across from it. The point of concurrency of the median is called the centroid. The centroid is the physical center of the circle. If we had like a rigid piece of paper, something that didn't, wasn't very flimsy, we could actually cut it out and lay it on top of, say, a pencil or something that was standing vertically. If we put the centroid on top of that, it would balance at that point, so the triangle wouldn't fall over. Next is the altitude. Now, one of the big misconceptions that I see as a teacher in a geometry class is altitude and height are very, they're synonymous with each other. You can say the height of the object or you can say the altitude of the object and refer to the same thing. One of the things that I recognize, though, as a teacher is that students often misconstrue height as being something that must go up and down. And the picture that we have here, this picture here that I'm adding to your notes is meant to show you that altitude does not have to go up and down. It's by definition, it is going to be the shortest distance from a vertex to the side across from it. So therefore, the only distance that is that way is something that creates a right angle. So here, all of these altitudes must be perpendicular to their bases. And again, base does not mean that it has to be at the bottom of a figure. And the last thing that we're looking at is the orthocenter. Now again, in the separate video that I made showing you the constructions of the altitudes, here in an acute triangle, you can see that the orthocenter is located inside of the circle, or I'm sorry, inside of the triangle. But with with the altitudes of an obtuse triangle, because this altitude here and this altitude here, they're actually not located inside of the triangle itself. The altitudes from the acute angles of an obtuse triangle will be outside of the triangle. That causes the orthocenter to be moved outside of the triangle, kind of like the way the circumcenter might be outside of a triangle for the perpendicular bisectors. Now here, this is, if you were to do a Google search or look up in a textbook, this portion right here is pretty much the only thing that you always get shown. That what they're saying is that the short segments, so here, let me just highlight one here, from B to F, that is a median. Well, if we look just at, say, this part right here, this is what most textbooks are simply going to refer to. Where the centroid is located, it's going to deconstruct the segment into two smaller, it's going to take the median and divide it up into two smaller pieces. So the larger piece, the segment from B to P, where the centroid is going to be 2/3 of the length of the overall median, which is what we're seeing right here in that first statement. But there's more of the ways that we could represent this, and there's more ways that you need to understand how these segment lengths relate to each other. The segment from the centroid to the midpoint is, so in this case, let me pick another color here. Let's see if yellow shows up okay. So now we're looking at this part right here. Well, what that is that is a third of the whole thing because, well, if the larger segment in red is 2/3 of the median, then the remaining portion must be a third of the median. And that is a mathematical relationship that we can exploit. It's not something where you have to say, oh, well, let's just look at the 2/3 part all the time. If I'm only looking at that small portion in relationship to the entire median, well, I just need to know that it's 1/3 of the whole thing. And what we're saying kind of here in this last statement is that the smaller portion of the midpoint, or I'm sorry, the smaller portion of the median, if it's a third of the whole thing, and the bigger portion is 2/3 of the whole thing, well, 2/3 is twice what 1/3 is. So you can look at it one of two ways. You can say that the small portion of the median from P to F, you can say it's half as long as it is from B to P. Or you could say that BP is twice as long as the smaller portion of the median. So that's kind of what we're looking at here. Make sure you have all of these additional things that I typed up in red here added to your notes here, because we do need to recognize them, and you will be asked to demonstrate your understanding of them. So now let's take a look at an example of how we're going to use those relationships. So here, point M is going to be the centroid of this particular triangle. And what we want to know, is, given the fact that from G to M, that it's 6 units long, how can we find the length of ML and GL? Now, for the time being, again, just focus on the problem itself. Try not to focus on what is typed up for you as far as just fill in the blanks. Let's just see, what do we know about it? Well, we know that the big bit from G to M, it's 6. And we want to know how long is it from here, from M to L. Well, according to what we just saw, the big portion of the median is twice as big as the small portion. So that means that the small portion here has to be 3 units long. So there's ML. So GL, the whole thing, well, now we can just add them together, or we could say, well, take 6, and since 6 is 2/3 of the whole thing, I can multiply 6 by 3/2, and that will give me the whole length, which we can just look at it here, and we say that should have to be 9 units long. So we can just think our way through the problem. Now let's see how how we're kind of filling in the blanks. Now what we're looking at first is they looked at the big bit first. They looked at from G to M first, which is fine. I would have simply just looked at it based, how I walked you through it right there, and said, well, if I know the big bit, then it's 6. Then the small bit has to be 3, so the whole thing has to be 9. Well, if all I know is that the big bit is 6, I can say, well, the big part of the median has to be 2/3 of the whole thing. So I set up the equation that says 6 is equal to 2/3 of GL. So multiplying by the reciprocal of 2/3 will give us 9. And then here, they're working it again a little bit opposite of how I thought about it, but it works the same either way. Taking the big bit and subtracting it from the whole thing gives us the smaller portion of the median to be 3. So that's how we're going to look at those median relationships. So what I'd like you to do now is try answering this question on your own. Still just talking about medians of a triangle. And when you have an answer and you want to check yourself against mine, go ahead and hit play again, and I'll be here waiting for you. Okay. So what we're going to be looking at here, FM is the big portion of the figure. So setting up the equation similarly to what they did in the other example, in example 1, I said that the big portion is equal to the 2/3 of the median. So to solve for the big portion, or to solve for the median, I multiply both sides by the reciprocal of 2/3, which would be 3/2, and I get FK to be 15. Now here, what I'm saying is that MK must be half as long as FM. So I just say, well, what's half of 10? And that gives me 5. Now, because the centroid does have a certain length that we can work with, there are things that we can do to figure out what they are on a coordinate plane. In fact, it's not something that I don't think that we will necessarily do, but it is something that I have done in the past, and it's very, very challenging for students. But we could, you know, we could set up triangles on a coordinate plane, and you would have to be able to find, say, where's the coordinate of the centroid using system of equations, meaning that you locate where the midpoint of two sides of a triangle are, find the equations of two medians of the triangle, and then set it up and solve it as a system of equations to find out what are the coordinates of the centroid. Now, this one isn't going to be nearly that involved, but it is still leading you down that path. So we have the vertices of a triangle, and whenever, even if they don't have a graph, what I want to do is I want to see uh, what does a triangle look like? Just give me some kind of shape, even if it's just a freehand sketch. I want to see what it looks like. So we want to find the coordinates of the centroid. So what I'm looking at here is I'm going to find the midpoint of one of the sides of the triangle. And now in this case, because of the way the triangle is set up, uh, looking here, if I find the midpoint of the long side of the triangle, you can see that from the vertices, or from the vertex here, and to the midpoint here, that they fall on a straight line. So that's really easy to see that I can count. I don't have to really necessarily do stuff with the distance formula, although sometimes I might need to. Okay, so since the centroid is 2/3 of the whole thing, let me go ahead and clear this up here. Then we can locate, looking at the length from the vertex to the midpoint, we see, well, it's 3 units long. So the centroid is 2/3 of the distance from the down the median. So if 2/3 of 3 would just be 2, so we can just plot the point here, and we can see, oh, there's where the midpoint is. Oh, I'm sorry, not the midpoint, but there's where the centroid is. Now, if we don't have these things set up for us where it could be kind of a nice length, if you notice here, from this vertex, we do have a horizontal line, but you see, because it doesn't quite hit here, this is going to be a fraction rather than a whole value. So I mean, we can still do the same thing. I can still say 1, 2, 3, 4.5, and I could take 2/3 of 4.5, and I'm still going to wind up right there. But uh, if that's why we kind of set it up to use the points that we did, so that way we could have a nice vertical line that gave us whole points to use. And again, if I really, really wanted to, I could find the oops, didn't mean to do that. Let's go back here. If I really, really wanted to, using the coordinates here, I could find the line of that yellow line. I could write the equation, y is equal to whatever, and then I could do, in that case, it would be y is equal to, or x is equal to 1, 2, 3, 4. X, so I could say x is equal to 4. That would be the yellow line. I know I'm writing it in red. But I could also find the midpoint of, say, like this side right here, and I could find where do those two lines intersect each other. So here I could say this is what, 1, 2, 3, 4. So I could also say y is equal to 4, and we could set up some system of equations. Now this one, normally they're in the form kind of like your point slope form. Oops, x. You'd have two equations in slope-intercept form or in point-slope form that you'd have to solve for x and then go back and solve for y. But again, we're not going to do that necessarily, but it is something that we could do. So I just want you to be aware of it. If you do encounter something like this in the future on, say, I don't know, the SAT or something like that. So here we have now we're moving on into the altitudes. Altitudes, again, they're going to go from the vertex to the side across from it and form a right angle because that's the shortest distance between them. And the point of concurrence in this case is known as the orthocenter. The orthocenter itself isn't anything that is particularly unique for our purposes. It's really just something that we're going to be can you identify it if you see it? Can you tell me what the name of the point of concurrency is? Since there aren't really any mathematical relationships in them, like there are with, say, the circumcenter, the incenter, or the centroid. So here it's asking you, can you find the orthocenter of the triangle? Now, what it's doing is it's kind of redundant. It's just saying, like, copy the triangle. I don't know why we didn't just do everything on the original triangles myself, but so what we're doing is you're going to just draw in the altitudes and see where they meet. So this is something that you would need a straight edge for, probably your protractor. Just measure the 90-degree angles. So what I had to do here on the triangle in B, the obtuse triangle, we did have to extend the sides of, so that way we could see the altitudes from the two acute angles, because the altitudes of the acute angles are going to be outside of the triangle. But on the right triangle, because the two legs that form the right angle, because they're already altitudes, all I had to do is just find this altitude right here and see that the orthocenter is going to be located right there. So that's really all this is asking you to do is, can you actually see where the altitude is going to be drawn, and see do they all intersect at the same point. So here we're looking at our last examples. I want you to go ahead and take a look at these. Question number 2, we're looking at the centroid again, uh, going back to the graph that we had. So here, where do you need to move point K so that the centroid is at a new point, 4, 5. So go back and take a look at that one. And using a compass, not a compass, but your protractor, find the altitudes of the triangle to see where the orthocenter is. So when you're done, go ahead and hit play again and see how your answers look against mine. All right. So let's see. Going back to example 2, point K is going to have to be moved to 0.49 in order for us to have the centroid located at 0.45. And when we come here to look at the triangle, because it's an acute triangle, the altitudes will all be inside of the triangle itself, and the incenter, I'm sorry, not the incenter, but the orthocenter should have been located somewhere right around here. So that's moving on here. Prove that the altitude to the base of an isosceles triangle is the median. Well, let's take a look at this. Why is this, oh, I want my pen still. Prove that the altitude to the base of an isosceles triangle is also the median. So what we were basically trying to show, why is point D going to be the midpoint? Well, looking at this here, and again, I'm just focusing on the triangle itself first. Let's just kind of ignore the fill in the blank stuff for the time being. Let's just focus on the triangle and see, can we think our way through it? Well, because it's isosceles, we know that BA and BC are the same. They're given to us because it's isosceles. One of the things that we know about isosceles triangles is that the base angles are the same, and side BD is shared between them. So we can say that for sure that the triangles have to be the same. Looking at this here, I'm looking here, I have a leg, here I have a hypotenuse of a right triangle. So I could say that the triangles are congruent at least by hypotenuse leg, or I could use the acute angle at A and C with the right angle, and side BD is the reflexive side shared between them, so I could show the triangles are congruent by angle, angle, side. So if the triangles are congruent, their corresponding parts must be congruent. So if A to D and C to D are the same length, then that must mean that D is the midpoint. And if D is the midpoint, then segment BD is also a median. So there's a couple ways that we could prove it. one with hypotenuse leg to show that the triangles are the same. Then we can show that the corresponding parts of the triangles are the same, or with angle, angle, side, however you wanted to look at it. So there's more than one way that we could think our way through it. So now that we have thought our way through it, let's just go ahead and fill in the blanks here and see what we have. Okay. So we know that those are an altitude, so they're congruent to, or so that they form right angles. The BD is shared between them, so at least we got hypotenuse leg. But again, we could have said angle, angle, side, using the fact that the base angles of isosceles triangles are congruent to each other. And here we go. So yes, and this is true for every isosceles triangle. The not only is it actually going to be, not only is the altitude also the median, but it would also actually be an angle bisector as well. Pardon me, excuse me. Couldn't help it. So here, why is it an angle bisector? Well, I kind of already just did that for you. Basically, we've already shown that the triangles are congruent to each other. So here's just a proof that I put together. Again, I prefer writing them as two-column proofs myself, but essentially we've already shown that I'm really just kind of taking the information that we already did and showing that, well, we have sides that are congruent to us that are given. We have angles that are congruent to each other because they're right angles, and we have a side that's the same because of the reflexive property. So the triangles are the same because hypotenuse leg. But again, we could have said angle, angle, side if we wanted to. So that means the angles at the vertex where point B was located, angle ABD and CBD, those have to be the same because corresponding parts are congruent. And so since the angle got cut in half, that means that BD has to be an angle bisector because that's the definition of what a bisector is. So just to kind of review, medians, those are pretty significant as far as the relationships of the segments of the median, where we have the big part and the small part. And the point of concurrency of the medians, of course, is called the centroid. That's the center of the triangle. And then the altitudes. Altitudes are, again, formed from the vertex to the side across from it to form a right angle. For right triangles, the two legs that form the right angle are also altitudes. And in an obtuse triangle, two of the altitudes have to be outside of the triangle, which causes, for those triangles, the point of concurrency, the orthocenter, to be located outside of the triangle. So those are the primary kind of high notes that we have for this particular lesson. Now, again, vocabulary. So you've seen a lot of vocabulary so far in this unit, and they all have different meanings. Mid-segments have certain properties about them. Perpendicular bisectors, angle bisectors, medians, altitudes, they all have unique things about them that are going to be very challenging. You will need to be able to recognize each of those segments if you see it in a diagram. You'll need to recognize what their characteristics are if you see it in a diagram, or if you hear it in a word problem. So, or if you just say, here's a triangle, show me where this thing is. You might have to be able to draw it and show me where it is. So it's very, very important that you understand the vocabulary, understand their, what concurrency points go with what segments, and what are some of their relationships that we can exploit with, an equation or right triangle, something like that. All right, guys. Well, thanks for watching. If you have any questions, make sure you let me know what they are. And until next time, guys, take care and be good.